Hello. In 1.3, we are talking about calculators and approximate numbers. In the beginning here, this first little paragraph, it says most numbers in technical and scientific work are called approximate numbers, having been determined by some measurement. Other numbers are exact numbers, having been determined by a definition or counting process. So for example, if we think of 12 iPhones that weigh 129 grams each, well, 12 would represent an exact number because that's how many iPhones are found by counting them. So 12 is an exact, it's found by a counting process. Whereas the weight of 129 grams each, this would be considered an approximate number because we're not quite sure how we rounded this. Maybe it was 128.8 or 129.2. It's not going to be an exact value, it's an approximate measurement. We will also be talking about two different things. We will be talking about accuracy and precision. Accuracy refers to the number of significant digits a number has, whereas precision refers to the place value of the last significant digit. What we'll do is look at some examples. We'll start with accuracy, and then we'll go back and look at the precision of each of these numbers. Rather than reading the rules, I will explain them to you as we go, and then you can read them yourselves. So for the first one, 2.36, we have an accuracy of 3 here. There are 3 digits in that number, a 2, a 3, and a 6. So the accuracy is 3, or we can say that this number has 3 significant digits. Number 2, 4002. This number would have 4 significant digits. Since it starts with something that's non-zero and ends with something that's non-zero, everything is counted and considered significant. So again, if it starts and ends with non-zero, we count everything regardless of what's in the middle. Now, here's where we start to have to be careful. When we have zeros at the end of a whole number. So here we do not have any decimals, so therefore these 3 zeros at the end, we do not consider them significant. So 5,000, that measurement would only have 1 significant digit. We are only concerned with the 5 here. Those zeros are not considered significant. Now, slightly differently, number 4 is 12.40. So notice how we have a 0 at the end, just like we did previously, but the big difference is there's a decimal here. If there's a decimal and you have a 0 at the end, it is considered significant. So just like we said before, if you have something significant in the front, something significant in the back, we count everything up. So this would be 4 sig digs. With the next one here, we have 2,000, and we have this little bar or tag above a 0. Typically, we see that bar to represent a repeating number. However, in this case, we don't ever repeat a 0. What this tag represents is it's making that 0 significant. Without the tag, this number would be 1 sig dig, just like the 5,000. But that tag is saying we want that 0 to be significant. So therefore, this value would have 2 significant digits. Again, these zeros at the end would not be significant, so therefore you have the 2 and the tagged 0. And the last one we have here, 0.0014. So this is not a whole number, meaning we have a decimal, but now there's zeros in the front. These zeros in the front are not going to be considered significant, very similar to why the zeros at the end of the 5,000 aren't considered significant. So this number would only have 2 sig digs. Now, if I were to add something like a 5 out in front of here, then you would have something significant in the front, something significant in the end. In a case like that, all of these would be significant. If, kind of just exploring another idea, let's say we had this 0.0014. If there was another 0 at the end of this, then that would be 3 significant digits because you have a 0 at the end of the decimal. These will take a little bit of practice until you get used to all the rules. We will use these to round all of our answers as we work through this entire class. looking at the precision of all of these. We look at the right-hand most significant digits, and then we say what that place value is. For example, 2.36 feet. This 6 is in the hundredths place. That way, or that would mean that the precision is to the nearest 1/100th of a foot. Number 2, 4,002. 2 is the right-hand most significant digit, and that's in the ones place, so the precision would be to the nearest 1 meter. 5,000 kilograms, the 5 is significant, that means our precision would be to the nearest 1,000 kilograms. Good, pause and try the next 3. 12.40 inches, well, the 0 is the right-hand most significant, and that's in the hundredths place, so it's to the near hundredths of an inch. This is in the hundred place, so it's 100 miles. And then we just want to be careful we count our decimal places out here. So this would be the tenths, hundredths, thousandths, 10,000ths, so tenths, hundredths, thousandths, 10,000ths of a gram. Okay, now what I'd like you to do in example 1 is you are going to look through these 14 examples, and I want you to just find the accuracy of each of those numbers. We're going to hold off on precision. We'll use that on the next page of examples, but go ahead and try 1 through 14 here. When you're finished, unpause the video and see how you did. Okay, what I would like you to do now is pause the video once again, go through and check your answers. Okay, just to kind of talk about a couple of these. You'll notice that what I often will do is anytime I see zeros in the beginning of a decimal or at the end of a whole number, I will always just put a little line through them so I don't get mixed up. So at the end of a whole number, cross those ones out, end of a whole number, end of a whole number, or the beginning of decimals. I always do that because those are never considered significant. Any other value is significant. Zeros at the end of a decimal, like here or here, here or here, are always significant. So beginning of a decimal or not, end of a whole number are not. Okay, now let's go to the next page to see how we have to use all this stuff within what we're doing in this class. You can read all these rules up here, but what they're saying is if you have 2 measurements that are being added or subtracting, we have to look at the place value. If we have 2 or more measurements being multiplied or divided, we have to look at the accuracy of those numbers. And that tells us how we need to round the final result. So for example 2, well, the instructions say perform the indicated operations with the approximate numbers and round using the rules for performing operations with measurements. We say approximate because if we were working with exact numbers, we would not take those into account for how many significant digits they have. So for example 2, 4,857 plus 73.8. Since we are adding here, then we have to use precision, because if you're adding or subtracting, you have to use precision. So we know that this one, let's just put a little P underneath it for precision. Use your calculators to add these, 4,857 plus 73.8. And when we do this calculation, we are getting 4,930.8. But when we look at the precision of both of these numbers, 4,857 is to the nearest whole number. 73.8 is rounded to the nearest tenths place. We will always round our result to the least precise. And that's what it says up here in this top part. Always go to the least precise, which would be to the nearest whole number. Therefore, we need to round our answer to the nearest whole number. So we look 1 to the right. Since it's an 8, the 8 rounds the 0 up to a 1. So therefore, our adjusted answer would be 4,931. And that would be our result. Example 3, 15.02 millimeters minus 12.6 millimeters. Again, we're subtracting, so we want to use precision here. Now, before we even look at the result, let's look at the place value of each of these numbers since we're using precision. This is to the nearest hundredths of a millimeter. This one is to the nearest tenths. So our result should be to the least precise, which be the one to the tenths place. So that tells us we need to round to the nearest tenths. So we type in our calculator 15.02 and we subtract 12.6 and we're getting 2.42 millimeters. But we want to round to the nearest tens place, which would be the 4. Look to the right. Since it's only a 2, we do not have to adjust the 4, so our adjusted answer would just be 2.4 millimeters. Make sure you include units when applicable. Example 4, 17.7 inches times 32 inches. So now we are multiplying, and if we're multiplying or dividing, we want to go by the accuracy of these numbers. Accuracy, remember, is the significant digits. So 17.7, that has 3 significant digits. 32 only has 2 significant digits. And we always want to go, just like we use the least precise, we want to use the least number of sig digs. So this tells us that our final result would only have 2 significant digits. We're not concerned with the place value of anything. We're only concerned with how many digits the number has. So we take 17.7 and multiply it by 32. When we do this, we get 566.4. And then we also have to remember inches times inches. That would give us inches, right, squared. Now, stepping away from that for just a moment, if we have 5 times 5, that could give us 25, or we could write that as 5 squared. If we had 5 times 5 times 5, that would give us 5 to the third power. That same method or idea here applies when we're working with units. Inches times inches is inches squared. Okay, back to this problem. So we already said that the least accurate has 2 sig digs, so our answer should only have 2 sig digs. And we always go from the starting at the beginning of the number. So we look to the right one. Since it's a 6, that's going to cause the other 6 to round up. So our adjusted answer would be 5, 7. However, what do we have to add to this? Right, at 0, because 566.4 needs to round to 500 something. So we have 570 inches squared. What you always just want to verify is that does this value have 2 sig digs? A 5, 7, this 0 wouldn't be significant. So yes, this has 2 sig digs. Go ahead and try example 5, then unpause the video to check your answer when you're finished. Okay, so find the volume of a cube whose edge is 8.50 centimeters long if the formula for the volume of a cube is V equals E cubed. So I wrote out that E is 8.50 centimeters, which is 3 sig digs. Remember, the zeros at the end of a decimal are considered significant. So we have to substitute 8.50 centimeters in for E. Well, if it's being raised to the third power, that means we have 3 of them being multiplied by each other. And then we take 8.50 multiplied by itself 2 more times. We get 6.14.125. Centimeters times centimeters times centimeters does give us that centimeters cubed. And since we have to go for 3 sig digs, we look at the first 3. Since to the right of that is only a 1, the 4 does not change, so it stays as 614 centimeters cubed. Now, example 6. For problems with multiple operations, we want to round the answer to the last operation performed. All numbers are approximate. Since this uses addition and we have multiplication division, we have to figure out if we need to use precision or accuracy. Before we just type this into our calculator to get the result, we need to look and determine which operation would the calculator be completing last. Here we have square brackets. Within the square brackets, we have this multiplication. So that would be one of the things completed first. Here we have parentheses with an addition completed inside of those. Once this multiplication is completed, once this addition, then we have to divide those two. Therefore, division is the last operation performed. So therefore, we do have to use accuracy for this problem. At this point, go ahead, type it into your calculator, find your result, and then round appropriately. Okay, when we type all of this into our calculator, we should be getting the result of 1.2544 and so forth. When you go to type this into your calculator, instead of using the square brackets, turn these into parentheses. and it'll make it a lot easier for you, and then you can type all of this in at once. Now, we have to determine how to round this. We said we have to use accuracy since the last operation is division, which means we have to identify how many sig digs each of these values have so we know how to round our answer. This is where the idea of approximate versus exact numbers come into play. It says all numbers are approximate, which means we want to look at each of these and consider them for our rounding. If there was a number that was an exact number, we would not be concerned with its number of sig digs. That would not affect the rounding of our answer. Here we have 4 sig digs, 3 sig digs, 2 sig digs, 3 sig digs. The smallest one of those is 2, therefore we need to round our answer to 2 sig digs. Well, since it's 1.25, that 5 causes the 2 to round up, so our adjusted answer would be 1.3. Good. Okay, this last one, example 7. I want you to pause the video, read this example, see what you can do with it, then unpause the video and see how you did. So before we get into finding the answer to this problem, we have to understand what it's asking first. It's telling us that we have a circular pipe. That would be this most inner ring. This is a pipe. It tells us that that pipe has a radius of r, which is 10.6 centimeters. So that would be that right there. That's 10.6. Squeeze that in. It tells us that the pipe has a thickness of 2.15. So thickness of the pipe would be this distance right here because that darker shade of blue would all be the pipe. So this distance right here is 2.125 centimeters. And lastly, it tells us that it's surrounded by insulation having a thickness of 4.8. So this is the insulation, and it tells us this right here as well. So this measurement right here is 4.8 centimeters. Now, this question is asking us, what is the outside diameter D? Now you can see it tells us up here that this is the diameter D. Well, that would also be the same distance that if we took these 3 here and put them together and then doubled it to get the other side as well, which means we have to take 2 times that radius of 10.6, add it to 2 times the pipe thickness of 2.125, and add it to 2 times the insulation thickness, which would be 4.8. So then you'd have to calculate that, and this question is actually telling us to round to 3 significant digits. So when you're done with that, round correctly and see what you get. Our final adjusted answer would be 35.1 centimeters. It would not be centimeters cubed because we're not multiplying them, we're just adding them together. Centimeters plus centimeters just remains as centimeters. Okay, that's all for section 1.3. Please reach out if you have any questions, and good luck with the homework.